Okay, so we were talking about the effect of torsion, bending moment, and shear on stresses. So if you remember, we can see here that in this example, we are revising several concepts from different chapters. So from chapter 3, if you remember, you studied the effect of torsion on shear stress distribution. And you have seen that a torsion moment will lead to the creation of shear forces within a certain distribution to create the torsion moment. And we have developed that the shear stress created at a certain location is torsion moment times the distance from the center. So here you have a couple around torsion moment around O that you computed, and then the shear stress distribution along the cross section will be T times rho, where rho represents the distance from the point of interest to center O over the polar moment J about O. And of course, for the polar moment, you have formula sheets that will give you for different shapes what is the corresponding polar moment. So this is what we are using from chapter 3 in order to determine the effect of torsion on shear stress along at a certain point. Now, concerning the effect of bending moment, for bending moments, then you can go back to chapter 4-5, where we considered the effect of bending moment on the normal stress distribution. And we have seen together that to create a bending moment in a cross section, we have a shear stress distribution given by minus my over I. And then we can use the, if you want, with our hand by determining the direction of the bending moment, we can know which side is subjected to tension and which one is subjected to compression. And finally, now from study of chapter 6, we have seen the effect of shear stress on shear force on creation of shear stresses along the section. And we have seen that to determine the shear resulting from shear stress, we have to compute Q. Q is the first moment of area about the neutral axis of the cross section. I is the second moment of area of the whole section about the neutral axis, or we call it also moment of inertia. And T is the thickness at the part of interest. So let's say if you have the following figure and you want to determine the shear stress at a certain location created by shear, we have seen together that the top and bottom level are characterized by Q equals 0, because the first first moment of area will be 0, since I don't have any area above this point. And if I take any other point, I should compute what is this area, what is its first moment about the neutral axis. I should determine the thickness at the cut in order to get the corresponding shear, where the shear is given by VQ over IT. So we will use all of this knowledge from the different chapters in order to be able to solve at a certain point what is the state of stress. So going back to our example, after remembering formulas we have gone over from different chapters, we can go back now to the problem we were dealing with. We already determined the state of stress at Q, and we said always to determine state of stress, you can select any element if you want passing by the point. And then you can, once you find the state of stress at for this, let's say, element, you can deduce for any other directions what will be the state of stress. This is why first you can select any element passing by K, but of course you should select the one that is easier to work with, as we mentioned, and which is then the free surface element. So for K we have considered this element, which which is subjected to 2D stress. Because if you take other elements, as we'll see after, like this one, for example, you don't have a 2D stress, you'll have a 3D stress to work with. So, and we'll see together how we can deduce 3D stresses, a function of once we know the 2D stress at one location, because when you change orientations, the state of stress will be different, and you can move from 2D stress to 3D stress in other elements. So always we try to select the elements easier to work with, as I told you, to get the state of stress in a certain frame. Once we get in this frame, you can deduce in other frames, x prime, y prime, z prime, what will be the state of stress. Now, we were done with point K, and we were dealing with H. So here's the free surface element is this one, as we mentioned, and we want to see the effect of torsion, bending moment, and shear on this element. So to do this, as we said, this part of interest, we can do the analysis on what is happening on this side. So to start with, H is a point of this cross section, and this cross section is subjected to a shear force. And if we draw this cross section, we can see that H is at the neutral axis of this cross section. So of course the shear stress at H will not be zero. It is it's a maximum value, because we have seen that on neutral axis you will have maximum shear stress due to shear force, because Q will be maximum in this case. So of course, if you remember, we said Q will be maximum if the cross section is constant. Okay, if you have the thickness constant. If the thickness is variable, we should do an analysis if it's maximum or not at the neutral axis. Okay, here just we can say that at this point, of course, we have a shear stress, and to determine, and of course the direction of the shear stress will be like the shear force. So it will be downward, and it is equal tau here will be equal to V times Q, which is the first moment of area of this area about the neutral axis, over the second moment of area or moment of inertia I about the neutral axis, of course, for the whole section, times the thickness T, where T is this distance, which is the diameter of this circle. So we have I is for the whole circle about neutral axis. We get it from formula sheet. It is equal to pi. Here, pay attention also here that you don't have a full circle, you have an annulus. So for an annulus, the value of the second moment of area, which is the inertia, is pi times r outer to the power 4 over 4 minus r inner to the power 4 over 4. The thickness I should take here is this thickness here. It's 2 times the radius. Here, please pay attention. Here, because you have an annulus, should pay attention that the thickness will be this one. So whenever you do the cut, you just have to take this part. It's not a full circle. Okay, should take this part and this one. This thickness here is r outer minus r inner. Okay, so T will be equal, and you have it at 2 levels, here and here. So the thickness will be 2 times r out minus r in. The shear force V is equal to the force applied, which is 10 kilonewton. So you replace V by 10 kilonewton. Pay attention for units, okay? So you can convert TV2 Newton, 10 times 10 to the power 3. And concerning Q, the first moment, moment of area is you should consider this part. Now, of course, you can go to the formula sheet. The formula sheet will give you, or if you want, you can say I can go to formulas of Q of a semicircle, and I take the outer one, Q of the outer one, minus Q of the inner one, and I get then the first moment of area of this part about the neutral axis. Once I'm done, I can compute tau at this point. Okay, and now I can say that the shear stress resulting from the shear force on H is in this direction, and I know now its value. So this is tau created by, if you want, shear. I should see what are the other effects on H. Okay, so we have considered the following elements. As we said, we'll consider this element, which is on the free surface. This is the effect of shear. Let us see now the effect of bending moment and the effect of torsion. For torsion, we already mentioned that this force will create a moment about y-axis, about positive y-axis. Okay, so now from torsional effect, the shear stress distribution at H resulting, the shear at H resulting from this torsion will be along, and if you do just this with your hand, you can see that this torsional moment will lead to a shear stress distribution at H in the section. Anyway, that at H you will have also shear like this, because this is along the rotation created by torsion. So we can see that we have superposition of effects. The shear stress direction is the shear stress created by shear force direction is similar to the one created by torsion, and since they are of same sense here, they will add up. Okay, and if in case they were opposite, you should take the algebraic values. So here, if you want, let us put the frame that we are working on for this element. For this element, you are working with x prime, y prime, where y prime is along this direction. This is y prime, let's say. Y prime here is equal to y of global axis. So here they are similar. The same for x. Okay. So here x prime or y prime are identical to x and y. And you can say that in this frame, if I want to represent my element now, so this is y prime, this is x prime. This is my element centered at H. I can see until now that due to shear, I have tau shear along this direction. So I should add tau shear, which is VQ over IT, plus tau of torsion, which is TC over J, where T is the torsional moment, C is the outer radius, because H is at the outer level. Here's the distance from the center, so it's 51 millimeter. And J is the polar moment about the center of the section. So for a circular, for an annulus, it's pi r outer square over 2 minus pi r inner square over 2. So tau torsion can be computed as the torsional moment T times here H is at this level here, at this level. So the distance from the center of axis of torsion is 51 millimeter. So it's r outer then. So I multiply by r outer over the polar moment. So if I take this section, let's say this is O, I get the polar moment about O, which is for an annulus cross section, it's equal to pi r outer square minus r inner square over 2. And now I still have the effect of the bending moment. So already we have determined that the bending moment here is along positive z, negative z, sorry. So this is the bending moment. The bending moment was seen to create compression at K, and it will cause tension on the other side. So here you compress K and you have tension on the other side. But because H is on the neutral axis of your section, it will not be affected by bending moment. Because you know, once I take a certain section, okay, I have a part subjected to, let's say here the bending moment is like this. So it's compressing K here, and it will do tension to in the upper point, but all points on the neutral axis will not be affected by the bending moment, because y of these points, or z here, z of these points is 0. Okay, any point on the neutral axis will not be affected by the bending moment. The shear stress on the neutral axis is 0. This is why I can say here that for H, the bending moment will not lead to a stress, which is opposite to the case of Q. Okay, so now if we want to plot the state of stress at H, we just have the following. We just have tau. We don't have normal stress. Okay, so we can put this. So this can be, this is called tau x prime y prime, and it's the and it's positive because, as you can see, it's along, if I take this face, okay, this is the normal axis is x prime, and its tau is along positive y prime, so tau x prime y prime is positive, and I add the effect of shear and torsion to get the total shear stress, and I can say that I don't have a normal stress, so I am in the case of I am in the plane of maximum shear. Okay, so here, sorry, for the plane of maximum shear, we have stresses, but I am in the case where I have a 0 stress, 0 normal stress, and I have only shear stresses. So if I want to consider now the state, I can write that sigma x prime equals 0, sigma y prime equals 0, and I just have tau x prime y prime. If I want to represent this, the state in a circle, if you remember, I can say this. So if I plot it, okay, so I don't have sigma x, I don't have sigma y, I just have a shear stress. Okay, so we'll see together how to represent such a state. And in this way, I was able to determine what is the state at H, and now I can deduce the corresponding values of the maximum and the minimum principal stresses and tau max. If I go back to this formula here, okay, here I have sigma average is 0. So I replace sigma x and sigma y by 0. I get then that the radius r is just equal to tau xy. Okay. And if you want here, I can deduce that my system can be represented by just a point where sigma x, sigma y 0, and I just have the shear stress. Okay.